Hi everybody, I'm going to show you the workflow of coupling light from photonic crystal fiber to free space, then to single mode fiber. So I'm Majid Ibn Ali Haidari from Ozen Engineering. So for this technique, I'm going to use the Lumerical Mode to simulate the photonic crystal fiber, and then a Zemax, Optic Studio Zemax from ANSYS to simulate ray tracing. So now we're going to use this photonic crystal fiber that you can see in this picture. So please follow my presentation on the YouTube channel regarding to dispersion engineering using optofluidic techniques, this structure. So what we can create our photonic crystal fiber by putting some holes in silica. So the blue is silica, and this air hole is this hole, white hole is air. You can see the photonic crystal parameter here. So this is D, radius, pitch, and other parameters. So for the engineering of photonic crystal fiber, the engineering of dispersion, we infiltrate the first ring of photonic crystal fiber. So please, for the more information, please refer to this reference, and you can get more information about how we can engineer the photonic crystal fiber. So actually, in my previous presentation, I showed that the dispersion versus wavelengths for different optofluidic infiltration. You can see, for instance, for refractive index of 1.32, if it's fluid with refractive index of fluid with 1.32, you can see that between the wavelengths of 1.2 to 1.6, you can see a flat dispersion. So because the dispersion is flat, it means that the higher order dispersion, like third order dispersion, first order, fourth order, so is zero. So it's better. So we start with this wavelength, 1.31 micrometer, and we can see here that we can see a flat dispersion. So actually, in this presentation, we've got two kinds of structure. A structure with wavelengths order like PCF, and free space component like lenses. So yeah, for simulation of like component with wavelengths scale, like photonic crystal fiber, we use a Lumerical, and we generate near field emissions, and then for the free space side, free space and ray tracing, I will use Optic Studio. Next, I will discuss how data is exchanged between Lumerical and Optic Studio using ZBF file. So you can see here. On the left side, you can see the photonic crystal fiber. Fiber output goes to the free space, simulated with Zemax. You can see here, this is a 2 lens. The thickness of each lens is 0.9 millimeter. And the space between two lenses is 2 millimeter. And once the ray tracing is done, we want to focus the light on this point, which is a starting point of single mode fiber. So light propagates through the photonic crystal fiber and single mode fiber by total internal refraction that you can see here. The core refractive index is larger than the cloud. It should be noted that the photonic crystal fiber, the air hole through the silica changes the average refractive index of cloud, which is less than core. And this is actually in the photonic crystal fiber, in this example, we have a modified total internal refraction. So, and also here we showed the output mode of PCF for 2 wavelengths. You can see here, and it's clearly that we can see that average refracting index varies as wavelengths. So our methodology starts with simulating the photonic crystal fiber in Lumerical, then saving the output file as a ZBF file, and then importing this ZBS file in a Zemax in physical optics propagation. Here. And we then optimize the actually optical system in terms of dimension, lens shape, thickness. And finally, we save the output of Zemax and then we'll import it again in Lumerical. So this is a hard walkthrough that I want to show you in this presentation. So let's continue to the software. So we go to the folder, open numerical file. So this is actually the structure that we've designed in my previous presentation. So this is Lumerical Mode. You see this is a silica. You can see the material. The material is silica, you see here. And you can go to the material and you can see material. You see this is a Selmayr coefficient. You can go to the material explorer, select the silica, select the index, select the wavelength range, for instance, 4.6 to 2 micrometer. You can plot. Imaginary doesn't matter because it's very small. So the real part, as you see, change it with wavelengths. So we want to work in this region. So the refractive index is around 1.446. And the fluid that we use is M2. You can plot the fluid also. As you see, M2, the refractive index of fluid is 1.32. So yeah, this is a structure, the whole structure, the holes through the silica. And this is the first ring that is infiltrated by fluid with refractive index of 1.32, the first ring. So this is the first ring. So this is a domain that we use asymmetric and symmetric in X and Y direction. So we can run the simulation. Change the wavelengths to 1.31. Calculate the mode. The mode is calculated here. You can see a nice mode. Here the effective index value, the wavelengths, the loss, group index, the polarization, and effective mode area. And again, for frequency analysis, you can do the frequency job. You can calculate the different parameter, for instance, frequency sweep. I do it again, frequency sweep. And so we have a different kind of curve, different kind of plot, effective index versus wavelengths, dispersion, and this is a group delay. This is dispersion. You can see here there is the dispersion value is around 1.31. It's very small. So we can right click on this blue button and then click to add selected mode to global deck. So this is a mode. Actually, this is a mode that You can see here, you can right click and save and select the Zemax beam file.zbf. So search, we can put in UCF, for instance, in Zemax. So next, we go to the Zemax. So we open Zemax file, pcf.zemax. Zemax. So I designed the Zemax file before, and to detail how we design and how we can use Zemax for optical system and optical device designing, I will describe in another presentation. So for this presentation, just I focus the coupling from the photonic crystal fiber to the free space optic, and then free space optic to the single mode fiber. So so this is the general view of Zemax. You see here in this site, you see System Explorer. You can define your aperture, your fields. If you need one field, two fields, you can add it by fields. You can tune your wavelengths here. For instance, here our wavelength is 1.31. That is the same as the Lumerical file, and you can define your unit. For instance, here our unit is millimeter, for instance. Yeah. So this is a lens data, and you can bring the lens data by this button, lens data. In the lens data, you can see how many surfaces you have. For instance, we have 6 surfaces, object, and stop. So this third surface is stop, and the last one is image. And so you can have a different type of surface. For instance, here you can select different type, but for this specific example, just we need a standard. And you see here there's a comment column, and you can change the radius as you wish. And you can you can put your radius as a variable, and this, and you can actually optimize your structure. Yeah, and this is a thickness, this column thickness, for instance, and you can tune what is the thickness and what is the thickness of the surface and the material. So we use a silica here for material, and chip zone, and so conic for different surface, can use it. So we work in a sequential mode, and by this button you can see the your lens structure. You can see here if I change the surface setting, you can see the color is changes. So I go to the surface 3, so you can see the color is surface 3. For surface 4 is surface 4. For instance, for surface 4, our aperture is a standard. The radius is 0.33. The thickness is 0.9, as I showed in the presentation. Because if you remember, I showed in presentation that we wanna use this structure The thickness of our lens is 0.9, and the space between the two lenses is 2 millimeter. So you can see the 3D viewer of the lens. Yeah. For instance, you can select symmetric, and you see here in a better view, you see, and for instance, this is a surface 2, see, this is surface 3, this is surface 4, and this is surface 1, and this is the last one, the same. So we can see that the thickness of lens is 0.9, the space is 2 millimeter, and the second lens is 0.9. And but you can optimum this structure, but just in this example, a specific example, we want to show the workflow. And yeah, and in the analysis button, you see that ray trace, ray aberration. Here you can see different aberration. You have aberration. But in this specific case, we want to focus on physical optics. So I click the physical optics. So in the physical optics, so in the setting, if you go to the beam definition and wanna see my file, my ZBF file. So my ZBF file is not here. So I must go to the fiber example. This is my ZBF file. I must copy my ZBF file to this folder, Zemax pop example here. And then now I can see the PCF in Zemax. So if I go to the select the beam propagation, the file, and here PCF in Zemax. So this is our physical optics propagation. But if you go to the setting, go to the general, this is a start surface, it's surface 1. End surface, if I select the surface end surface as a surface 1, just this is a start of the beam that we import to the Zemax. So you can see that this is our profile. Also, you can see this profile from the beam viewer. You can go to the PCF in Zemax, and you can see the beam viewer, and you see different parameters here, like that we imported in the Zemax, and you can see also the text file. So let me go to the close this viewer. And so now in a different surface, we can see our output, for instance. If I go to the surface 2, see, changes by this way, and go to the surface 1. In image 1, we can see this picture. Now, if I save the output file of Zemax, PCF out, we can save it as a PCF out Zemax. But before, so I save it, but you can go to the fiber data, and you can, based on fiber coupling integral, you can change your waist of X and Y. For instance, for this specific case, we go to the vertical side, and you can see here, I go, see this one. So it's 4.2 or 4.2 micrometer, for instance. You can put the, but you can calculate the structure, but in this case, it's not my main concern to calculate the different modes. Just put it, for instance, 4.2 micrometer, 4.2 micrometer. Save it, and then go to display and save the ZBF file. And okay. So now, if I open my single mode fiber files like this, and this a single mode fiber that I want to couple the light here. Now we have a mode in this region, and I want to see the mode overlap between the single mode fiber and the fiber. So the output of Zemax. I bring the output of Zemax. Let me the simulation. So calculate the mode. Oh, I can load the file. Again, we must bring the file from Emacs to our current folder. So now I load the file. Go to the overlap analysis. You can calculate the overlap here. So next, we can use the output of Zemax to the Lumerical FDTD, and you can calculate the FDTD simulation on it. So show you. So this is the Lumerical FDTD. You see here, because we don't need to put in a structure, just we want to show a workflow. So this is a FDTD. You can go and we can see the layout mode. And now we can see the FDTD, that geometry, mesh setting, boundary condition, all of the boundary conditions, PML. We can put our source. We can put source here, and but our source is we must import the field to the source section, and this is monitor. Just have two monitor. So for the source, if we right click on a source and click edit object, and we go to the import source, then change here to the ZBF file. This is the output of Zemax selected, and then we say that the data has been successfully imported. So we click OK, select OK, and then select OK. And now we can run the simulation. Yeah. So we're waiting to simulation. Yeah, simulation is finished. So you can see here in the source section, we see a electric field and magnetic field. It means that the data comes from the Zemax to the to the numerical side, you have all of the information of electric field and magnetic field and all of them. For instance, for electric field, you can right click on field and new mode. And the mode that we bring it to the actually numerical, and this is H, and we can see that the intensity of H is much lower than the E. So we can see the different monitor here, but those monitor is not important for us. So just we see in this simulation, we see in this workflow that, so we start with Lumerical Mode, we simulate the mode calculation, and we export the mode to the Zemax, to the free space, and in free space, we've done some simulation based on the physical optics, and then after ray tracing, import it to the Lumerical Mode and Lumerical FDTD. And in the Lumerical FDTD, we see that which information we have: electric field, magnetic field, and all of the information that we can write our script and do our simulation. So let's come back to our slide. So we defined this workflow and we know how it works. So, but what is the new opportunity for us? The new opportunity is that, for instance, imagine that in the Zemax Optics Studio, I have an optical system, like this lens is here and this lens here, and this is a surface that we can put our diffractive grating on it. For instance, 1 diffractive grating. It means that this 1D diffractive grating must simulate with Lumerical, but the ray tracing simulate with in Zemax. And for instance, this is for two-dimensional case, here. This is a one-dimensional Bragg grading, this is two-dimensional. And by this case, by combining the one-dimensional and two-dimensional, we can increase our field of view. We can improve our, for instance, augmented reality and virtual reality systems. And for instance, we can define meta lens. You can find a good example regarding to this application in an ANSYS website, and it's recommended to study this kind of application. So what is the workflow? So this case is not actually included in this version, but in the next version that coming soon. Actually, you don't need to exchange the data manually, as you see in this example, in this application, that we import the Zemax file from Lumerical to the Zemax and then Zemax to the Lumerical. Because in the diffractive grating and for instance, in 1D and 2D diffractive grating or meta lens, for instance, you can actually Lumerical and Zemax dynamically work together. And you see here, this is Optical Studio. There is a DLL plugin, you can call it. And, it's actively working. Optical Studio called the Lumerical. And the Lumerical do the simulation in a wavelength scale and just, return back the data and just, do this kind of routine and jobs to optimize and find the best structure. So you can find, for example, in this application, as you can see here, and there is this is a, for instance, 1D grading, and this is a 1D grading, And this is a 2D structure that you can see here. And they are detector. So by this case, you can increase our field of view and other parameters. So you can find a good example regarding to, for instance, Lumerical and Zemax for meta lens, fiber lens coupling, Lumerical plus Zemax. For ray set data, Lumerical and Zemax. You can find this kind of application in Lumerical in ANSYS website. So actually, as you see here, ANSYS software's tools cover the photonic case, Lumerical FDTD, Lumerical Mode, multi-physics, Lumerical interconnect, and the optics studio. And so we can see here is Zemax. Oh, just in this presentation, we showed an example workflow between Zemax and Lumerical FDTD or Lumerical Mode. So that's it. I think we covered this presentation, the title of this presentation. Please contact us. This is our information, Ozenic Engineering. And so our office in Sunnyvale. So you can contact to support@ozeninc.com if you need more help, if you need if I can help you, I'm happy, I'm very glad. And this is our office in the map. And thank you for your attention, and thank you.